Welcome to a course on complex analysis. In the previous lectures, we have seen the concept of analytic functions, and in this lecture, we are going to see the concept of harmonic functions. With the help of harmonic functions, one can construct analytic functions. How we can do these things? That is what we are going to explore in this lecture. The topic of today's discussion is harmonic functions. So this harmonic function plays an important role in applied mathematics, like in temperature problem and allostatic potential problem. In these problems, these type of harmonic functions plays an important role. First of all, let us start with the definition of a harmonic function. So the definition tells us that a real valued function So we take some real valued function. By real valued function, we mean the codomain of the function is the subset of real numbers or the set of real numbers. Okay. So what is the domain of this function? This is a function of two real variables, namely x and y, which means this is a function which is defined from R2 to R, or some subset of R2 to some subset of R, that may be of any kind. Okay. So these kind of function is said to be harmonic in a given domain of the xy plane. So in our course, till now we have been saying about complex plane, z plane, but here we are saying it as xy plane. So this is where the difference lies. Okay, in xy plane, x-axis is x-axis, y-axis is y-axis. Whereas in complex plane, x-axis is real axis and y-axis is an imaginary axis. Okay, there is a slight difference in that. So that is why here we are saying it in xy plane. If throughout that domain the function has continuous partial derivatives of the first and second order, and it satisfies the partial differential equation. So that is second derivative with respect to x plus second derivative with respect to y is 0. Okay, this equation is known as Laplace equation. Right? Any function which satisfies the Laplace equation is known as harmonic function. So if we have to talk about a Laplace equation, actually this is a Laplace equation in two variables. Okay, so we may extend the Laplace equation for any number of variables, but here we are going to talk about only functions of two variables. Now let us see an example. So which is some example from applied mathematics. So the first one, we are given a function t of xy as e to the power minus y sin x. Okay, and this is given in the vertical strip, in the semi-vertical strip. Okay, 0 less than x less than pi and y is bigger than 0. So this is some semi-vertical strip. So if you try to plot the semi-vertical strip, you may very well see if this is your axis. Okay, so with axis x and y, right? So in the xy plane we are talking in your axis. So your x has to be from 0 to pi. So this is your point x is 0. If this is your point pi, then you have some line like this. Okay, why? Because in 0, so this quantity, so this goes something like this, and this is like this. Okay, here this is going, sorry, here it is not a bounded one, so this goes this way, right? And it assumes the values. Okay, here along with this we are given few more informations about t is equal to sin x on this end, and t is 0 on this end, and t is 0 on this end. Okay, first of all, here our interest is to verify whether this satisfies the Laplace equation or not. So what is tx? Tx is e to the power minus y cosine of x. Txx is e to the power minus y multiplied with minus sin x. So this becomes minus e to the power minus y sin x. Then ty is minus e to the power minus y sin x, and tyy becomes minus of minus e to the power minus y sin x, and this becomes simply e to the power minus y sin x. Thus txx plus tyy is 0 from the values that we obtained. Okay, now the problem is your txx of the function of two variables plus tyy xy, this is equal to 0, and from the diagram you may very well see that whatsoever the value of y is, if your x is 0, so your 0 comma y is 0, and similarly t of pi comma y is also 0, and t of in the place of x you may have anything, and when your y is 0, so this is sin x. And limit y approaches infinity t of xy. So from the t value and from the diagram it is evident that it is 0. Okay, so this system, okay, are these equations describe steady state temperature in a thin homogeneous plate in the xy plane, and that plate has no heat sources or sinks and is insulated except for the stated conditions along the edges. Okay, so the example that we have seen here is purely some applied oriented example. Now we will see some mathematical aspects of these harmonic functions. So here we have a theorem, and this theorem tells us that if a function f of z, that is u of xy plus iota times of v of xy is analytic in a domain D, then its component functions u and v are harmonic in D. Okay, so in order to prove this theorem, the basic assumption that we are going to make is that without loss of generality, or some, we can say what, so okay, we shall have the components, the real and imaginary parts of the analytic function possesses continuous partial derivatives. Okay, so real and imaginary parts of an analytic functions. We are not talking for differentiable functions, we are talking for analytic functions. Okay, so the real and imaginary parts of analytic functions possess continuous partial derivatives. So why are we saying this? So from this, what we are coming to say here is second order derivatives of u and v exist. Okay, so this is the key point that we would have to take from the result that we have stated here. Okay, now let us start our proof. Assume f is analytic on D. So if f is analytic in the domain D, then CR equation has to be satisfied. Okay, so from which we shall write ux equals vy and uy equals minus vx. So let us have them as equation 2. Sorry, have them as equation 1. Okay, so differentiating both sides of 1 with respect to x, we get uxx is vyx and uyx is minus vxx. So let us have the test equation 2. Now let us differentiate both sides of 1 with respect to y, we get uxy equals vyy and what, uyy equals minus vxy. So let us mark this as equation 3. Okay, so by continuity, uxy is same as that of uyx and vxy is same as that of vyx. Okay, because the result that we have stated here tells us that the real and imaginary parts possess continuous partial derivatives. So the existence of derivative is there along with the continuity of the derivatives as well. So from which we write these things. Therefore, uxx plus uyy, that is what uxx is vyx minus vxy. Because of the continuity, this is 0, and vxx plus vyy. So vxx is what? Minus uyx from equation 2, plus this is uxy. Again using the continuity, this is 0. Hence, u and v are harmonic in the given domain D, and this completes the proof. Okay, so now let us see a few more examples. So this is the second example in harmonic functions. If you consider f of z to be e to the power minus y sin x minus iota times of e to the power minus y cos x, we may prove this function is an entire function. Okay, so in order to prove this is an entire function, let us look for the what CR equations, right? So my u, okay, here first of all, what is my u? So my u is e to the power minus y sin x, and v is minus e to the power minus y cos x. So my ux is e to the power minus y cos x, and vx is e to the power minus y sin x, and uy is minus e to the power minus y sin x, and here vy is minus of minus, that becomes plus e to the power minus y of cos x. Thus ux is same as that of vy, and uy is same as that of minus vx. Therefore u and v, like f satisfies CR equation. Also, we observe that ux, uy, vx, vy exist, and they are continuous as well. By sufficient condition of differentiability, the given function f of z is differentiable at all points of the complex number, which implies f of z is analytic in entire finite plane. So here by finite plane I mean the z plane. Okay, the entire z plane, it is analytic. Hence f of z is entire function. Okay, is an entire function. By the previous result, by the previous theorem, we conclude u, that is e to the power minus y sin x, and v, e to the power minus e to the power minus y cosine x, are harmonic. Okay, the next example tells us that f of z is iota upon z squared. Okay, clearly this function is analytic in any domain which does not contain 0. So if the function does not contain the point origin, then in the domain, okay, so in the domain the function turns to be an analytic function. But still, this function has lot to study, and that is what we are going to do in the next lecture. Thank you.